Welcome back. In this section, we'll talk about intermediate Scala collections. We'll start by talking about additional collection types, then talk a little bit about basic mutability with builders. We'll talk about some interesting collection features, a bunch of the methods that are part of the simpler methods that we talked about in the first volume, but that provide a whole lot of value on their own. Then we'll talk about sorting collections and some of the various ways that you can do that and helpers that exist to facilitate different ways to sort collections. And finally, we'll talk about intermediate for comprehensions and some of the more advanced things that you can do with those. We're going to start by talking about additional collection types. We'll only be talking about immutable collections for now. First, we'll talk about vector versus list, then we'll talk about map, and finally, we'll talk about set. Let's get started. First off, keep in mind, as we've discussed before, that all of the collections that we're talking about are immutable. That means that you are not changing the collection in place. Rather, you are getting back a new collection every time that you make some sort of modifying action, and that new collection has whatever changes you've made. The old collection remains untouched. So if I create val A, and it's a list of 1, 2, and 3, and I then decide to add, say, 4 to it, I get this list back that's got 1, 2, 3, and 4, but the val A is still referencing a list with just 1, 2, and 3. So when we added that 4, we got a new list with everything that was in A plus a new one. Now, the way that list works, this basic class, is that it's a linked list. So that means that internally it's actually represented by links in a chain. So internally, list 1, 2, 3 is one block that contains 1, followed by another block that contains 2, followed by another block that contains 3, followed by another block that contains 4. And if we create an extremely long list and we try to add to it, depending on which side we're adding to, it can be very fast or very slow. So let's take a list, call it my long list, and we're going to do this by taking the numbers from 1 to 100,000 and turning them into a list. So we'll give that a second. We've got my long list. And we're going to try adding a number to the beginning of my long list and see how that goes. And then we're going to try taking my long list and adding a number to the end. Now that felt like it took about the same amount of time. This is a good illustration of the fact that computers are very fast, and you often have to go to very large numbers to really see some of these differences. So we're going to try 1 to 1 million. Creating that was still pretty fast. We're going to try 1 to 10 million. There we go. So now this is taking a minute to actually build it. And so we have this long list that's got 10 million elements in it. Okay, that's a lot of elements. Let's try adding something to the front of it. 0 followed by my long list. So we can see that it took a little bit. And this may actually be taking some time just to display. So if we've got 0 followed by my long list, let's see if it takes any different amount of time to add 0 to the end of my long list. Now you can see from that pause, it actually takes significantly longer. In fact, we ran out of memory trying to do it. So what is happening here? Why is this taking so much longer? Well, the answer is that when you have a chain like this, 1, 2, 3, 4, 5, in list, you actually only have a reference to the beginning over here. So my long list basically points to this 1, and then we know that it's a list, so we know to traverse until we get here to the end. And in Scala, the way that this is typically represented is this double colon. So 1, 2, 3, 4, 5, other stuff, and then finally you've got nil at the end that indicates we've got an empty list, we're not traversing any further. Well, when I try to add something to the beginning, all I have to do is come to the beginning over here, look at my long list, I look at 1, and I stick this 0 in front. But if I'm trying to add to the end, I start at 1 still, and then I go to 2, and then I go to 3, and I have to get all the way to the nil, and then I have to add the 0, and then this is actually a new list for the end of all of this. So I have to copy all of these elements and point each of them to their new version that points to 0 at the end. So it's a very, very slow process. To deal with this, we have another type that can handle situations like this more easily. It's called a vector. So instead of my long list, I can do my long vector, and we'll still go 1 to 1 million, or to 10 million, I believe we said, and we'll say to vector instead of to list. Let's see how this works out. It's still taking a good amount of time to actually construct it. In fact, I think we killed ourselves on memory before, so let's try exiting and come back and rebuilding it. There we go. That happened very quickly. So now we've got this long vector, and I'm going to try adding this 0 to the front, my long vector. You can see that was very quick. Then I can try adding it to the end, 0. Same, maybe even faster. So what's happening here? Vector represents things in a much more optimal way. So basically it allocates big chunks of memory, and it uses those chunks of memory to insert things anywhere that it needs to. So it actually builds a tree, what's actually called a trie, and uses this trie to be able to find a place to put things very quickly. So it can find the beginning and can find the end, and it can find anywhere in the middle very quickly as well. So let's talk about another limitation of lists, and we'll start fresh with some fresh memory again. We'll declare my long list again, and this time we'll try to get to the 500,000th item. So my long list dot get lets us add an item at a particular index, 500,000. That's at, my mistake. We'll start over really quick here. Scala, recreate my long list. We're going to build this 10 million item list, and then we're going to try and look up the 5 millionth item. We can look things up in a list by just using the parens, invoking it as a function. 5 millionth seems to have looked up pretty quickly. Let's see what happens if we try to look up past the end. Index out of bounds exception, but you saw that took a little bit. It didn't go quite as fast as the other one. Let's see what it takes for us to look up the 9,999,999th element. I think I may have missed a 9. Oh no, see, that actually worked relatively quickly. So lookups are actually pretty fast in lists because we traverse them very quickly. Let's try this with a vector though, my long vector. We build this same vector. It's going to take a little bit, and we actually don't have the memory available to hold both the vector and the list. So when you deal with big lists like this, you can run into some limitations. Let's create ourselves this vector again. Goes very quickly, and then let's look at the 500 or 5 millionth element. Again, lookup is very fast, 999, 999, 9. So what's not immediately obvious here is that if you want to look up an element in the middle of a list or towards the end of a list, it can be quite slow. Now lists show their slowness the most when you try to insert something at the end or try to insert something in the middle because they have to do a lot of copying. Vectors work very nicely to insert stuff at the beginning, to insert stuff at the end. You can also use the patch method, and you see that patch takes a from, a patch that is a sequence, and a replaced number. So what does that mean? Well, what I can do with patch is, I've got this long vector, and I can take the slice from 5,000 to 5,005. If I look at that, those numbers are 5001, 5002, 5003, 5004, 5005. What I can do with patches, I can say, okay, starting from index 5000, I want you to insert 1, 2, 3, 4, 5, and I want to replace 5 items that way. So now, if I go back and look at the same slice, note that we're going to get the same thing, because the original vector is still immutable, so it still didn't change when we did this patch. Instead, res4 now holds a new vector that has this change in it. So we'll do this same slice, but we'll do it on res4 instead. Now, 5000 to 5005 has 1, 2, 3, 4, 5 now. In fact, let's look at 4999 to 5006, and we'll see that everything else remains unchanged. Now let's see what happens if we say patch and we change this 5 to a 1. So now we've got res 8. And let's take this same slice, 4999 to 5006. What do we get? Well, now we see 5000, 1, 2, 3, 4, 5, 5002. So what happened was we said at index 5000, patch this sequence in, but only replace one item. Now replacing one item means item 5001 was replaced by this sequence, and then 5002 remained unchanged. Earlier, we said replace 5 items. And what that meant was that 5001, 5002, 5003, 5004, 5005, all 5 items were replaced by the items in this sequence up here. So this means that patch gives us the ability to insert something in the middle without changing anything around it, or replace certain pieces of what we're seeing in the middle. We can also specify something longer here. So if we do this, res10.slice 4999 to 5006, you'll see we've got still the 1, 2, 3, 4, 5, but because this was longer, we actually deleted 10 elements and then inserted the 1, 2, 3, 4, 5, and so 5001 through 5010 are all missing. So patch gives us a powerful way to update vectors midstream. That's all we're going to talk about around vectors in this particular section. The important thing to remember with vectors is they are faster to insert into the middle of and at the end of. They're faster to update. They've got this patch helper that reflects the fact that they're so fast to update and let you make changes in the middle of it. And they are faster to access in the middle of as well, although oftentimes the differences in access are not necessarily human perceivable, but they can be very important if you're doing access into the middle of a vector in a tight loop or something like that. So that's vectors and lists. Let's talk about maps. Maps are a basic data type. They map one type to another. So let's say string to an int, and we'll name this one ages. And we'll map some ages to some numbers. Now the way you construct a map, you type map, you open a paren, and then you type tuples. So the tuples that go into a map are basically the bits of the map that you want to insert when you create it initially. So Cleo is 10, Santiago is 8, and Roger is 18. So you see these are just regular arguments. Notice that I'm using this arrow. For simplicity, let's actually first talk about using a comma. So this is just a tuple, and that means that it's just a thing that always has two elements in it. Once we instantiate it, you see that it's still represented in this tuple form, but it's got no parentheses and it uses this arrow. That's because that is a shortcut way of defining tuples. So I don't need the parentheses if I use that arrow. And so I can declare this like this immediately if I want to. Just like that, it works exactly the way that the other version did as well. That saves us having to type those extra parens. We have to type the arrow instead, but it's a little easier to read. It's a little clearer to understand that we're mapping Cleo to 10, Santiago to 8, Roger to 18. If we want to get the age of anyone, we use .get. We get an option back. So if I .get something magical that doesn't exist, we'll get a none back. And if we use apply, which is what happens if we can either invoke it directly by typing apply, or we can treat ages as a function, we get a no such element exception instead. If we use apply and we pass a key that does exist, then we'll get the value without the option wrapping it. Usually you should be using get. Get is the safest way to do it. And what you'll find yourself doing sometimes is you'll want a default. So you'll want to say ages.getCleo, and then you'll use get or else, which is the option function, to say otherwise, if it doesn't exist, then we'll return -1. And so magical, same thing, but this time we'll return -1. And that way you go from an option int to an int. What you often find is that you will need this enough that someone has considered it and created a convenience function for you, and that's the case with map. So there is a get or else directly on map where you can pass two parameters. One is the key that you're getting, and one is the default that you're looking to return. Just like that, we've skipped this .get followed by a get or else charade, and it works the exact same way. It's really a matter of style if you want to use the shortcut version or if you want to use this one. This one sort of interacts with more primitive types. It's a little bit clearer that get will return an option and get or else will do this, but at the same time, it's really nice to have this convenience and be able to type a little bit less. The other thing to keep in mind is that you can add to map midway if you want to. So I can add John, who's 58, and I get this map back. Now we've got Cleo, Santiago, Roger, and John. Now, just like before, maps are immutable. So ages still contains just Cleo, Santiago, and Roger. Res22, the result of evaluating this bit, now contains Cleo, Santiago, Roger, and John. So we've not touched the original ages map, we've just created a new map that contains all that stuff plus one more element. Maps behind the scenes will kind of often decide some optimal ways of representing themselves, but for the most part, you can assume that they'll be using a very similar representation to vector. It's also based on a trie, and it works similarly quickly on insertion and on retrieval. So we've got adding stuff, we've got looking stuff up, we've got one more thing, which is deleting stuff. If I wanted to remove Cleo, I could just use minus. So we just use regular math operators and they behave exactly like you'd expect. Res22 minus Cleo gets us a map that has Santiago, Roger, and John. You can also use, even though map is a little bit special, even though it's kind of got these pairs in it instead of individual values, the way that list and vector do, you can still use regular collection functions like for each, like map, like flat map. Let's look at using map really quick. If we did ages.map, and we looked at parameter and we printed it, let's look at what this parameter is. So each iteration, we get a tuple with the key and then the value. So the interesting thing here is, and by the way, we come out the other end with a list of unit, because basically println returned unit for each one of these elements. So we get a list out here. Now, one very interesting thing that we can do is apply pattern matching. So this parameter is a tuple, and so we can extract name and age directly using a pattern match, an anonymous pattern match. We don't have to do any extra dances here. We don't have to declare more than one case. This will catch every possibility. And so we can return anything we want at this point. We can do this. And what that'll do is turn our map of name to age into just a list of available ages. So if I wanted to get all of the ages without caring about the names, this is one way to do it. I can also change this so that we change the key. So I can return a tuple if I want to input a map and get a map out the other end. So I could do name the funny age, and out the other end comes a different map. This time the keys are Santiago the funny, Cleo the funny, Roger the funny, and the ages are unchanged. I can also change the age if I want, plus 12. You do need to have this parens around here. Now we've got Cleo the funny, Santiago the funny, Roger the funny, and each one of them is older. Lastly, you can change these types completely, so I can flip the whole map. Instead of going from name to age, I can go from age to name if I want to. And once we run that, we see 10 to Cleo, 8 to Santiago, 18 to Roger. The only thing to keep in mind is that maps can only map a single value to a given key. So you can have as many keys as you want as long as they're different. So let's say instead of this that I tried to map everyone's name to the value 0, to the key 0. If I run this now, I see that I get a map with just one element in it. It's the element at key 0, and it gets Roger, which is the last one of these that we saw. So we started, when we mapped through, we mapped Cleo to 0, and then we mapped Santiago to 0, which overwrote the previous entry, and then we mapped Roger to 0, which overwrote the previous entry before that. So we end up with just a single element map. There's one more convenience function. In the case where you're just trying to change the values and you're not interested in the key at all, you can do ages.mapValues, and that will just pass the value for each key in without giving you the key. So we just get the age, we add 12 to the age, and out the other end comes, again, a map. We keep the keys intact, and we modify their values along the way. So that's map. Pretty easy as well. Finally, set. Set is a data structure that can only hold one of a given element. So, my ages. Say I have 12, 18, and 28. This set has 12, 18, and 28. It can only contain each of those once. So let's say I tried to add, using the regular plus operator, 18 to it. The resulting set still has 12, 18, and 28 in it. That's because a set can only contain one value once. If I try to add 19 to it, I now have 12, 18, 28, and 19. Perfectly normal. Then, if I wanted to subtract 19, it would go away. Note above, we added 18. Let's say I try to subtract 18. Now we just have two elements in the set, 12 and 28. The way that this works, if I add 18 and then remove 18 and it started with 18, I end up with no 18. So I started with my ages, which was 12, 18, 28. I tried to add 18, but it was already in there. So I still ended up with a set with 12, 18, and 28. And then I subtracted 18. You can do set addition and set subtraction, which is typically done as an efficient way of combining sets and separating them. So if I had my ages versus dog's ages, and in this case it will be 1, 4, and 9, I can combine these, my ages plus dog ages, using the plus plus operator, which you can always use to combine any two kinds of collections. And I get 1, 28, 9, 12, 18, and 4. Notice that the order is now completely different. Typically, sets do not preserve order. So the way that sets efficiently determine whether something is already in the set means that they do not efficiently keep the order of the elements. So all we know with a set is, does it contain something or does it not contain something? We can find that out very fast. We can ask my ages dot contains 12. And it'll get back to us very quickly. If we ask .contains 8, it'll get back to us very quickly. But when we combine two sets, when we get into longer sets, the order here is just going to be whatever it's going to be. It's not something that you can rely on or work with. If you care about the order, you have to track it separately. So we looked at my ages plus dog ages. We got res40 that has both ages. And we can also subtract a different set. Say, I don't want 28, 9, 12, 16, 32, or 89 in res 40. This trims us down to 1, 18, and 4. So 28 goes away, 9 goes away, 12 goes away, 16 doesn't exist in the set, so it's not affected. 32 doesn't exist in the set, so it's not affected. 89 doesn't exist in the set, so it's not affected. Notice that because of the way that this is set up, subtracting this set from res 40 and subtracting res 40 from this set does not produce the same result. Instead, it's a quick way of determining what is in one set and not in the other one, or vice versa. There's one last thing that we can look at, which is that with set, as with map, as with list, as with vector, you can use the map function. So let's look at res 40 and map each of its elements to add 10 to it, and we'll do this with the shortcut. Here we have an element for each element that was in res 40, except we've added 10 to each of them. So 1 became 11, 28 became 38, 9 became 19, 12 became 22, 18 became 28, and 4 became 14. We just add 10 to all of them. The interesting thing about this is that our set still has only one element for each possible value. Now this is guaranteed no matter what, so if the map produced a collision basically, we'd still end up with one element in the resulting set. So maps can be done on all collections, but they work a little bit differently depending on the semantics of the collection. That's all we're going to talk about right now.